Thanks, everybody. Great to see you all. Really happy to be here. I would have enjoyed being at Berkeley, but I'm also very happy to be here at Stanford. Different sets of hikes to do, which is nice. Yeah, so yesterday Charles told you about something about the geometry of information and entanglement, and today I'm going to tell you something about the flow of it. So we've hit both topics. And the basic thing I'll tell you actually two results. The first result is about the speed at which information spreads in generic chaotic systems. So I'll pose a sharp question, which defines a velocity in the simplest case, and then I'll tell you how that velocity relates to other observables that we're interested in. And then in the second part, I will discuss some kind of interesting interplay between sort of the simple motion information as you would have in like an electromagnetic wave, and then the more complex motion of information that occurs in that chaotic system. It's motivated by a sort of puzzle in black hole physics, which I'll describe. It's not clear it's the resolution of that puzzle, but it's at least an interesting phenomenon in its own right, I think. All right, so let's set the stage. Standard way to think about communication between two parties, say Alice and Bob. Let's suppose they share a quantum state, which is indicated by this black line here. And what Alice can do is she can apply, say, some unitary operations, x sub a, depending on whether she wants to send 0 or 1. And then the system can be allowed to evolve for a while, and then Bob can measure in some fashion and try to figure out what Alice said. So like Alice makes a radio wave, the radio wave propagates to Bob, and Bob measures it with an antenna. Pretty standard. And okay, it's an easy calculation to show that the probability that Bob gets B given that Alice sends A relative to the probability that Bob sees B when Alice did nothing is just related to this commutator here. So this is like something that should be pretty reasonable to you, commutator related to linear response, for example, in quantum mechanics. So it's just really telling you that you shake the system here and you ask how much of a response you get over there. But I wanted to draw your attention to one fact, which is that this is some particular matrix element of a commutator. And this matrix element could, in principle, be small in a system which is chaotic or thermalizing. So the information is not lost, of course, but it's ultimately unitary, but it may be hard to see what Alice did over here if you're only allowed to make local measurements. So let me formalize that a little bit. So we can sort of consider the case of, roughly speaking, weak versus non-weak interaction. In the weak and interacting case, like think about electromagnetic waves, you can excite some localized wave packet. The wave packet moves some group velocity, say, and then the other party can make a local measurement, and the commutator, even the matrix elements of it, can typically be large for such kind of free field systems, or weak interactions. On the other hand, you could imagine that you're playing with some interacting chaotic system, like a QCD plasma or something like that, and in that case you could inject energy or do some local operation. But typically there are no long-lived coherent excitations, so there's not much to carry the information. And although the information is ultimately there somewhere in the system, it's not easy to tell what you did from a local measurement. And one way to see that is that this matrix element of these commutators will typically be very small after a relatively short period of time related to the relaxation of the system. Okay, so this sort of naive signaling picture you have here is not really going to work because you make a signal here, kind of dies out, and then if you look over here, you just see like thermal noise. Okay, but that's fine. It's still possible, if we change our way of thinking a little bit, to diagnose how this information that you injected into A is spreading in the system. And the idea, a simple way to do that is to sort of tag it in a sense with some entanglement. So imagine instead of putting some information in here, what you do is at time 0, you have here, say, one-dimensional spin chain here. And you take some extra ancillary qubits, a reference, that you entangle maximally with the first site here. It's decoupled from the rest of the system. And then what you're going to do is you're going to let time evolve on this system here. just put the reference in a box, nothing happens to it, it sits there. You let this time evolve in this system, and what will happen is if it's chaotic and interacting sufficiently, that this entanglement within the system will spread out in some way, indicated here by this sort of purple box. And we could ask, sort of as a function of time, how big a region do you need to have access to recover that entanglement? So this is, like I said, a way of tagging the information, so to speak, and sort of tracking how it's moving in the system. It's clear that if you have the entire system, you can obviously recover the entanglement. You just evolve backwards in time, and there it is, right at the start. But in fact, it's possible to recover it at some later time from a small subset of the system. And our goal here is to calculate the minimum size region, this purple thing here, we would need to have access to and complete control over to determine or to extract this entanglement back out. Okay, I claim that that region is typically going to expand ballistically in the simplest case, and I'm going to define the speed of that expansion to be the information speed vm. Okay, so my goal is to calculate this speed. Any questions about the setup? Okay, so here's the setup more precisely. I'm going to consider some state of the system, some initial state, which is typically out of equilibrium. It doesn't have to be, but it will often be. It has some energy density epsilon, which you can think of as a proxy for the temperature, the thermal state that it would approach at late time. And it'll also have what I'll call the entanglement fraction f, which means that it can have some initial entanglement which may not be maximal. So the entanglement of a subregion A at time 0 would be the volume of A times the entropy density, the thermal entropy density, times this fraction. So f equals 0 would correspond to a product state or an entangled state like the ground state, and f equals 1 would correspond to a state that's sort of fully entangled and looks like thermal already at the start. Okay. I'll say this is sort of a toy model. There's definitely other terms like area law terms, etc. here, but I'm going to sort of try to abstract that away and give you a very simple picture of the entanglement structure. So this is the kind of model we have in mind. We have this initial term here, which is a fraction of the thermal entropy. And then we're going to assume that the entropy also grows in time, proportional to the thermal entropy density, the area of the region A, time, and then that defines the velocity, which we call the entanglement velocity. And in fact, it turns out that this entanglement velocity will depend on the fraction f. It doesn't just give the same value no matter how much entanglement you start.
Sorry, why is the same entropy density shown up in the growth term, or is that just a unit?
This is the definition of what this V is, if you like. So, in order to, this is a dimensionless, so this is, linked to the d minus 1, that has 1 over length to the d, and so you take all those factors out, you get a velocity. The physical intuition is that this formula really is only valid for some short time at which you reach local thermal equilibrium, and so then the effective number of local degrees of freedom that are evolving or processing is the entropy density. And yeah.
Is this saying at local equilibrium, then they will just reduce to the butterfly velocity?
Yes. So you're getting ahead of me, but yeah, that's it. And so that characterizes the entanglement structure. Again, I emphasize this is a toy model. I've extracted away the area law pieces, subleading pieces, early time, late time, etc. I'm focusing on a particular region in space-time diagram. And then the other thing we need is that there's operator spreading, which moves at some speed, VB. It turns out this speed is independent of the fraction as far as we can tell. It does depend on the energy density. And the claim that I'll make is that these two numbers are the only thing you need to know. No other detail of the state matters after early time if it's sufficiently chaotic.
How do we determine this entanglement fraction?
That's something you sort of input, like it's how you choose your initial state. So you could put a product state in which case f equals 0, or you could take a product state and evolve it for a very long time, then add the entanglement after that, that will correspond to f equals 1, or you could do something in between and try to get some different fraction. Make sense? Okay, with this setup, I claim the following is true, that the information velocity is the minimum of the entanglement velocity divided by 1 minus f and vb. That's it. Okay. This is the result that we had in this very recent paper with Stefan Eccles, Josiah Couch, Fu Nguyen, and Shenglong Xu, and myself. And the arguments is kind of fun. It actually just boils down to Hayden-Preskill or some variant of Hayden-Preskill. The idea is something like this. If you want to know what the minimal region that can recover the entanglement is, an equivalent way of saying that is to ask for the maximal complementary region that cannot recover it. So you just do the negation. But then the idea is that complementary region is entangled with the thing you want to recover from. And so I can apply Hayden-Preskill in various situations to conclude that I can recover the entanglement in that complement. That means I can't recover it in the region itself. And this is a way that I can just figure out by tracking basically how far the operator has spread and how entangled the system is. I just determine which regions can reconstruct and which cannot. Okay.
Brian.
Yes.
One of the results of the Snaven paper was that the butterfly velocity, well, the spreading of operators is always faster than the spread of entanglement. Right. And so I'm wondering why there's, you need to pick the minimum of one of these two.
Yeah, good question. Actually, thanks for bringing that up. I'm going to talk about this a little bit more later, but let me say it here now. So this minimum comes from the fact that there are in principle two bottlenecks in Hayden-Preskill. You need to have the scrambling and you need to have the entanglement. So in principle, a priori, either of those could be the bottleneck, and that's why there's a minimum here. What we actually find is that this is always less than or equal to that. We can actually prove that with some plausible assumptions. And actually this asymptotes to that as f goes to 1. Okay, so it's a very nice package that puts everything together into one box. And if you're familiar with this literature, like going back to the original paper of Josephine and Hong, what they call the entanglement velocity corresponded to VE of 0, where the entanglement fraction was 0. You start from a product state. Okay.
So according to your definition, the information doesn't spread out until if you have a finite system, until it encompasses the whole system, it spreads out until it encompasses half the system and then stops.
Well, so it's spreading always as a function of time, and I'm just tracking how far. And then, yeah, eventually once it gets to like the whole system, if it's a finite size system, then it'll have spread everywhere.
But it'll spread everywhere, or just half is enough to recover?
Yeah, half is always enough for half plus a little. Once it goes beyond that. Okay, so let me give you an example to kind of hopefully clarify what's going on here. So let's take the case f equals 1. So as I said, I'm going to start with some like very highly entangled thermalized state indicated by this blue blob, which is touching all the rest of the spins. And then I entangle, say, the first spin here with a reference at time 0. So this state you can think of as essentially being already thermalized. It's a pure state, but it looks thermal locally. Then I evolve in time, and the entanglement here spreads, as I said. And the basic idea is this. So there's a butterfly cone, which sets how far the local perturbation that you apply here is spread in the system. And the idea is, suppose this purple region were smaller than that butterfly cone. Well, then I have two pieces of information I know. First of all, the rest of the system here is maximally entangled with that sub-region, the purple region. And I have a little bit of that scrambled output, which I'm also able to access because I have a little bit less of this purple region that I control, so that means that's in the complement. So I have a maximally entangled state, I have part of the scrambled output, and therefore by Hayden-Preskill I can recover the entanglement with the reference in these uncolored black dots plus a little bit of the purple. Let me say that again. Think about the situation where this purple region is restricted to say these middle 5 dots here. So I have these 2 dots and these 2 dots which belong to the rest. Well then this black region is like the memory in Hayden-Preskill. It's entangled with the remainder of the purple. And I have a little bit of the scrambled output here, which comes from this butterfly cone. And the memory plus that few bits of scrambled output is sufficient to recover the entanglement. Since I can get it in the complement then, minus a little bit here, that means I can't get it inside the purple region. And so I must need a region at least as big as the butterfly velocity times time to recover the entanglement. On the other hand, I'm not going to need more than that because that's like the speed limit in the system anyways. So it's very natural that that is the right scale. Yeah.
Since you're talking about the stuff that's related to this naming stuff, I guess one question, maybe you'll talk about this later, but how robust are these statements to like random noise, like measurement noise? Because like this complementary thing is very dependent on the overall process that is running being unitary.
Oh, you mean if it's open system dynamics? Oh, well, yeah, then it's a different story. If it's like just random circuit, it's probably fine. If there's static disorder, it'll slow things down. So there's various ways you could modify this. You could add static disorder, which will slow things down, and then you may not even have a speed anymore. You could add unitary fluctuation, like, random circuit kind of noise or disorder, which I think everything would still work. Or you could open the system up and then the information just leak out into the environment. Typically, this would all be moved. No part of the system would be able to access it. Yeah.
So just so this argument seems to depend on the presence of the scrambling.
Yeah.
And so you can't really apply it to the case of electromagnetic waves or.
Indeed, yeah. Yeah, maybe this wasn't super clear. This is like a separate case. So the electromagnetic wave case would be very different. You wouldn't have this structure. There'd just be like a wave packet. And if you have that wave packet, you can recover the entanglement. And if you don't, you can't. So here.
And is that a special case of your formula or your on the previous page, or is it?
I wouldn't really say so because I think like VB is not really defined, for example, and I don't really thermalize and things. So yeah, I think maybe there's some relation, or I could generalize it somehow, but I wouldn't say it's really at this stage some case. Okay, so that's the case when it's maximally entangled to start with. Now, more generally, this top panel is the version of Hayden Presley you might be more familiar with. We have this memory which nothing is happening to, and there's some scrambled region here. And the idea is very simple. We're just going, once we don't have maximal entanglement, we're going to dynamically generate some of the memory. So the scrambling dynamics will generate the memory, it'll entangle, and it'll also spread the information, and the interplay of those two effects is what gives the transform. Okay, so here's the argument. So we have this condition. First of all, let's assume that this VE is less than VB times 1 minus F. You can actually prove that with some assumptions using relative entropy, comparing various thermal states. This is a generalization of an argument of Kamijetti and Hartman. And what this implies is that operator spreading is not the rate limiting step except when F is equal to 1. So the rate limiting step is always making the entanglement. And so then we just need to track the effective size of the system and memory for using Hayden-Preskill. And sort of the key point will be if we look for a region, we sort of scan over region size. So we make the region bigger and bigger and bigger until we find a region whose entropy is just saturated. Then the effective system plus memory size will be twice that size because the region is just saturated, and then everything else which is entangled with it, which I may as well just compress to an equal size system at no cost to myself because it's all acting in the complement. So then the story is relatively simple. If the region you have control over is bigger than that saturation region, it means you have the whole system plus part of the memory, and so of course you can recover the entanglement, or of course the remainder of the memory cannot recover it. And if the region you have access to is smaller than that saturation region, then the memory plus the extra bit of A sat minus A has maximal entanglements plus part of the scrambled output, and so again, by Hayden-Preskill, it can recover the information. So then all we need to do is figure out how big this saturation region is as a function of region size and time. Well, if you take that formula I wrote down a couple of slides ago and compute saturation time, it's going to scale with the region size of the subleading terms, like region size times 1 minus F divided by entanglement velocity. Then if you take the limit of large size and time, where this formula really makes sense, you get this simple formula that I claimed, which is the entanglement velocity divided by 1 minus F. So it's just basically asking how long it takes to saturate the entanglement of the subregion. And that's the rate limiting step. I should say I'm sort of describing this as if it were like a interval. All this goes through for like strips and higher dimensions. You can do other shapes, but then it's a little bit more complicated because different things can happen. But anyways, this is the simplest case. And that's it, okay? Now, that's kind of a general argument, but it relied on a sort of abstract and simplified model of the dynamics. So let me show you that it actually works in real systems. So here's a spin chain. For spin chain aficionados, this is a standard Ising with transverse longitudinal field. And what we've done is we've just simulated this numerically with 22 spins using some Krylov technique. And over here on the left panel, don't worry too much about this, I'm just showing the mutual information between the reference and various subregions as a function of time for different cases where f is 0 or 1. The important figure is the right here. What this figure shows is as a function of the fraction f, which we can engineer in the initial state, the information velocity plotted here. The black line is the information velocity extracted from taking these curves and looking at the place where the mutual information is half of its maximal value. So it's like the inflection point where you go from having no information to having a lot of information. It's possible that's, has some finite size error in it, but anyways, it seems to be a pretty good definition. So that's what this black line is. The blue line is an independently measured entanglement velocity, which we just get by studying how the system entanglement grows with time. And this blue line is that entanglement velocity divided by 1 minus f, and you see that it's just basically on top of each other. Until you get up here to larger f, where we start to be dividing by something small divided by something small, numerical errors start to cause problems, and we can't really say, we're not very confident that the numerics on this small size is accurately capturing the physics there. And then this VB up here is independently computed from some large size tensor network method. So all three of these things are independently computed. There's no fitting parameters, and they just essentially agree perfectly at least at low f. And I'm pretty confident that if you dial this up to 100 spins, you would just see that they line up with each other essentially perfectly. Okay. Now we can also do a holographic calculation, which I'll just describe very, very quickly. You can set up this kind of initial state in a two-step fashion. You can start with a thermal field double state for some particular energy density, epsilon naught here. And you can add a shock to one side, which adds some extra energy to take you up to energy density epsilon. And then the idea will be at the fraction, which is the ratio of the actual entanglement to the thermal value at the final energy density, will just be the ratio of these entropy densities at the initial energy and the final energy. Okay, so we can control this very easily just by dialing this initial thermal field double state. And we can, of course, control the final energy density by just deciding how much energy we throw in this shock. And so we can just explore this whole parameter space of states. We're going to do the reference part by just adding a particle that's entangled with a reference. Okay, so we just imagine injecting a particle with some spin or something, and that spin is entangled with some reference system. And then the rule, which just follows from the rules of ADS-CFT, is that any region whose entanglement wedge includes the infalling particle can recover the entanglement. That's it. So we just detract these regions, and as always, our goal is to find the smallest such region as a function of time. A version of this calculation was done for the case of thermal state, f equals 1, by Bizet and Stanford, and what we did is sort of a vast generalization of their calculation. So let me give you an example. Here is the ground state of the system, empty ADS. This blue is a shock. In this case, it has energy and charge. We did that because it's possible by varying these two knobs independently to make the ratio of V and VB be very different, so you can just explore a bigger parameter space. This green line here is the particle I threw in, and this is just the Penrose diagram of some ADS resonant Nordstrom black hole. Okay. And so the basic idea is we pick some time here on the boundary, and we have various candidate HRT surfaces, which could tell us what the entanglement wedge is. There are equilibrium surfaces where this would just go in some distance and stop somewhere in the static region, the outside region. And there are out of equilibrium surfaces where it would penetrate into the pre-shock region. And this out of equilibrium surface will have a time-dependent entanglement. The equilibrium surface will correspond to time-independent entanglement. So thermalization is like switching from this out of equilibrium surface to an equilibrium surface as a function of time. Okay, and so when I draw this picture, it's actually, if you imagine that I sent the particle shortly after the original shock that set this thing up, well then the basic point is that as long as this surface which dominates the HRT calculation is the out of equilibrium one, the one that goes inside the pre-shock region, well then it's always going to intersect this green line, you'll be able to recover the entanglement.
Sorry, this means the concurrent patch of the vacuum? Or?
Yeah, this is the vacuum down here, and then this is the charged black hole up here. And this is the shell which separates the two. And these are the singularities. So basically, if this thing goes inside, which means the entanglement is still changing, you can recover it. That means the region is big enough, so its entropy is not saturated yet. That precisely agrees with our previous calculation. And if the RT surface is now outside in the equilibrium region, then it won't touch exactly this very early time particle, and you'll just get that it doesn't intersect the info thing, and you won't be able to recover. Okay. So that was the ground state example. I think it hopefully illustrates simply how this works. You just track which regions have this intersection, which regions don't. And I just say, I won't go into any details of the calculation, but we can do the general case. First of all, you can write down a formula for the entanglement velocity in this thing. It does in fact depend only on the fraction F and the energy density epsilon. It doesn't depend on the charge at all, or at least not directly. So that's one confirmation of the claim I made earlier that only those two parameters matter. And we can compute all these things independently. We can compute VE analytically. There's a formula there. We can compute VB. It indeed doesn't depend on the fraction F. And we can numerically also find these regions by just searching through which HRT surfaces are saturated or not. And all those things agree with each other. And indeed, they go down from VE to VB, or VE of 0 to VB in this nice curve, just like that. And this all follows just from this one. Okay, so the story works. It works for spin chains, it works for holographic models. There's a sort of general confirmation picture of why it should work. So we feel pretty confident conjecturing this is a pretty general description of the speed of information flow in these kind of chaotic systems. Okay, I'll make a few comments. One thing I like about this is that it unifies VE and VB in one setting, which I think was sort of an annoying feature before. It also gives us a very simple way to understand the entanglement wedge dynamics in terms of a just Hayden crystal, basically, or some slight variant of that. And also in the paper, which I won't talk about, is that you can generalize this first wormhole story to this case, where what you do is you send a signal at one point and you couple somewhere else far away, and then it's the butterfly velocity, because it's own. This is in the case where f is equal to 1. It's open whether you could generalize this to other values of f. But in that case, then it's just the butterfly velocity, which sets like the time for the information to come out again on the other side. Okay. Great. Okay. So, any questions about this?
So,
Yeah.
if I have a system with different degrees of freedom propagated with different speed, let's say just I interact like two systems on top of each other with different VB and VE. In your definition, will VB be just the faster one of the two?
I think in that case, it would depend on whether you're looking at the physics before or after they've come to like mutual equilibrium with each other. If they really don't talk, then it's like this setup does not apply. If they do talk, then after that like equilibration timescale, I would think it's more or less the faster of the two speeds that would determine things.
I thought that your inequality still applies because like even if they don't talk to each other, VE will be like an average or something, but VB will be like the faster one if you look at the commutator. I think that's like the separation of degree of freedom, but you don't know.
Yeah, that could be. That could be. I haven't thought carefully about that. But that could be. Okay. Other questions? All right. Now, yeah.
Is there any statement that can be made about local thermal equilibrium? If I take a thermal state, but I perturb it, and then I would expect that sort of inside the light cone, you'll get back to local thermal equilibrium. Is this telling you at all where that, where that is? Sorry.
Yeah, I think so. I mean, it's telling you, well, for example, it's telling you that equilibration happens more slowly than you thought. Like if they give this operator speed VB, but actually information spreads much more slowly in principle at this VE speed.
Yeah.
So that it's actually not spread nearly as far as you would have naively thought in a situation where there's separation of scales.
Okay, but inside the VE cone, I should expect an essentially local density.
I think that's right, yeah.
Okay.
And yeah, that's a great question actually, because it also relates to one of the reasons we thought about this, which is that we're trying very hard to design classical simulation techniques that can describe sort of thermal equilibrium systems without having all this entanglement built in, a sort of effective local description. And so it would matter to know sort of or what scale and what region size you have this kind of local description. So thanks for that question. Okay, in the last little bit, I will talk as far as I can about a kind of an application of this, but an interesting twist on the story. So I want to talk about a little puzzle of sorts that Peter Shor raised, which has to do with the way black holes process information and some seeming conflict between scrambling and the black hole spacetime geometry. So what Shor said to do was, let's think about a Schwarzschild black hole. Later I'll think about a sort of ADS radius size black hole, ADS CFT, to use the technology there. But for now, let's just think about Schwarzschild black hole. He said, okay, as a function of Schwarzschild time, let's think about breaking this space-time up into cells to find by requiring like the light crossing time to be of order some fundamental time scale, which would just be like the light crossing time or the temperature, the inverse temperature, right? And then, so we have some time scale for dynamics and we have some entropy. And we break the space up into these cells, like little computational cells. And you can do a little calculation that says if you have order 1 fields, then you would expect each of these little cells to have order 1 bits in it, or quantum bits. And so Shor said, let's just abstract away all the geometry and just have this little cell model, like a little computer around a black hole. And let's ask to what extent that could process information in a way consistent with what we expect from, say, ADS CFT or some other expectation. And we're going to declare ignorance about the quantum gravity dynamics that you might think take place near the horizon, for example, like in a membrane paradigm kind of picture. Except we'll make one crucial constraint, which is that these dynamics, whatever they are, have to obey the speed limits of the black hole spacetime. Okay, that's it. This is kind of what it looks like, not to scale, but this is the basic picture. The rough idea is if you take like the Rindler metric and you divide out by the for the time coordinates, just hyperbolic space. So this is just essentially hyperbolic space here. The number of cells increases exponentially if you go in. And if you set a cutoff at some proper distance, a Planck length from the horizon, you have sort of order entropy shells here. So this is, for example, if you had a view that maybe the black hole entropy was all coming from like Hawking radiation of the stuff outside, this would be like a picture you could draw to convince yourself that the counting was roughly right. Okay, and then what Shor says is, okay, this is a nice setup because in the setup I can show 2 things. First of all, he distinguishes what he calls weak and strong scrambling. Weak scrambling is sort of like what time order correlators measure. It's like scrambling localized small amounts of information. And he says in this case, it is possible to scramble weakly across this whole system in time tau log s. The basic idea is you can go, say, from here in log s steps out to here, then you can go anywhere around the black hole in order 1 time unit and then go back down. So it's like a ballistic missile trajectory. And this way, if you actually did, say, a random circuit dynamics on this graph, you would actually have a scrambling time in the OTOC sense of order tau log s. However, we could talk about something stronger. We could talk about strong scrambling, which is asking that if you started with some initially out of equilibrium state, where say the northern hemisphere and the southern hemisphere were under entangled, they had less than their naively maximum amount of entanglement, we could ask how long it takes to generate that maximal entanglement. And kind of remarkably, just from the structure here, I'm showing you a two-dimensional version, but it works in any dimension. You can argue that time for that strong scrambling would be about tau times s, or tau times s to some power. That's a pretty long time. That's much longer than this time. Okay. And so, okay, what Shor said, if I interpret him correctly, is that, okay, fine. No one ever really said that this was a short time scale, or at least that's what he said. Maybe it just takes a long time to do strong scrambling, and weak scrambling can still happen, and that's mostly what we thought about before, and so there's no real issue. Okay, problem is there is an issue, at least in ADS CFT, because if you have one of these ADS radius size black holes, same kind of picture will apply roughly, except beyond this region, instead of going to flat space, you're going to asymptotically ADS.
Can I ask a question?
Yeah.
Why do you expect or care about scrambling outside the black hole, as opposed to degrees of freedom?
I think it's, yeah, maybe what I should say is that I don't think this is actually the way it works, but this is like a counterfactual we're setting up to say, so like somehow this is like quantum filtering, and maybe in this final layer there's something funny going on, something complicated.
I think it's almost, right? Because as long as dynamics at the last scale is local, which may not, but as long as that's the case, this is a model, right?
Right. Okay.
Because, yeah.
So yeah, I don't think this is right picture, but it's like an. Well, I'll argue it's not right, but.
Oh no, not sure thing. This block.
Yeah. But yeah. So I think what Shor is sort of saying is that if you think of all the essential physics that's happening in some possibly complicated dynamics in this graph, which obeys the locality properties of this graph, it cannot possibly have a strong scrambling time shorter than that. Yeah.
I think maybe one way to be maximally favorable to Shor would be to say that if the membrane itself was not bound by the speed limits of the quantum field theory near it, that could translate in some situations in faster than light communication from the point of view of the outside. If you set up the black hole state just right, so the membrane transfers something from one black hole end to the other. I don't know if that would be such a big problem. But,
Raphael's very smart, so as you'll see here. So first, let me just make the point that there is a problem.
Surprising development.
You can calculate ADS CFT. You can actually set situations up where there is a black hole that is significantly under-entangled, and you can compute the time scale for it to reach the strongly scrambled state. And it's short. In fact, it's time of order tau in the simplest case, and certainly not tau times some power of the entropy. This is a calculation that we did recently in some other context, but also a previous work by Hartman and Maltese. Okay, so the challenge then is how do I reconcile these two pictures? Like, what's wrong with Shor's model? And what I want to say is that what's wrong with it is that you don't actually respect the space-time structure of the black hole, at least near the horizon. But it doesn't cause any problems. That is, photons or other weakly interacting degrees of freedom will still respect the causal structure of that space-time, even though there's some degrees of freedom that are moving information around much more rapidly. So it's sort of like we go back to Einstein and we say, how do we even define what we mean by space-time geometry? Well, we do it by shooting light rays off of mirrors or whatever far away and timing them and making some network of rods and clocks. If we made such a network of rods and clocks using these simple degrees of freedom, we would get an ordinary space-time geometry out. But nevertheless, you can sort of glue in or attach in something that's moving complicated forms of entanglement you can't easily observe much more rapidly. So here's a sort of toy model. You have a ring here, which I think of as simple, like just free fermions, say, or free photons, or whatever. And signals can propagate, but they take a long time to go from this side of the ring to that side of the ring. And now what I'll just do is I'll glue in some other crazy thing. Each of these outer black dots talks to some inner red dot, but the inner red dots have a totally non-local interaction between them. I'm going to think of these as roughly like the horizon quantum gravity membrane degrees of freedom. Okay. And the key point will be that there's three physical effects that occur. First of all, the signals that propagate here are attenuated by their coupling to this bath. Second of all, the bath allows entanglement and operator growth to proceed very rapidly within this thing. But that very rapid growth is not easy to observe from the point of view of someone, some brave soul probing this black hole. What they would need is to be able to reverse time or have multiple copies of the system or do some other very complicated kind of interaction. They can't do that. And so then there's finally a possibility that some coherent signal here could tunnel or somehow move through this bulk and come out the other side. That would be bad. That would mean we don't really have the geometry we think about. But what you can argue in this case is that the amplitude for that to occur is suppressed by powers of the system, so these powers of the black hole. I'm not necessarily claiming that's a strong enough suppression to agree with what you expect from quantum gravity, but it's a model. In fact, well, anyways, I won't go into the details. And we can actually see this in a small size simulation. Here I'm going to have a 20-site chain and a 20-site SYK with open boundary conditions. And I'm going to look at the response, the commutator, or in fact the anti-commutator between one end of the simple chain and the other end of the simple chain. The black line is what you would get from the free particle propagating. That's the outer black dots. The dashed line is what you would get for the case where this is all-to-all interactions, but they're two-body interactions, not four-body, so there's no chaos. And the red is what you get in the case where there's chaotic interaction. So you see in this dot-dash case where there's all-to-all connectivity, but it's not chaotic, you immediately see at early time some significant violations of the causal structure. That is, some signal can actually come out the other side, and you wouldn't attribute this to a local space-time geometry which obeys the speed limits of the space-time. But if you turn on chaos, if you go from 2 to 4, well, then it adheres much more closely to the causal structure until it starts to diverge in some way at later time.
Sorry,
Yeah.
fragments are opposite sides of the...
I made it an open boundary condition, so just I'm a chain, then another chain where everyone talks to everyone. By contrast, if you look at the entanglement, well, this black is the decoupled outer ring. So it increases for a while, and then it actually goes down again to this integral, some oscillations or funny business going on. But the Q equals 2 and Q equals 4 have a more rapid entanglement growth that actually stays larger as a function of time. So the message is that the Q equals 4, the chaotic all-to-all interacting thing, has a causal structure similar to the free case, but entanglement growth like this non-local situation. And so we can, in fact, have our cake and eat it too. We can have the causal structure that we want as far as simple probes are concerned, but we can also spread complicated kinds of entanglement very rapidly. So there's no real contradiction between these two things as long as we're willing to tolerate this kind of funny business on the horizon. Okay, so that's it. What I told you about is sort of distinguish these two kinds of information motion, the sort of weakly coupled, like electromagnetic wave type, and then the strongly interacting chaotic spreading type. I told you about a result that we have on the way that the speed of the spreading in the chaotic case. And then I use this interplay of these two different types of information, spreading or motion, to propose a kind of potential resolution, or the skeleton of a resolution, to this sort of issue that Shor raised about a naive tension between space-time locality and the way information is processed in the black hole. Okay, and I think I should probably stop there. Thank you.